So in this last note video, I'm going to explore two example problems just to kind of show two different problem types. One of them is going to be super fast. We're just going to have a rational exponent instead of a regular old square root. And then we're going to do one that involves a little bit more work. So for our first example here, let's look at the integral of dx over the quantity x squared plus 1 to the 3/2 power. Right, so that might not at first scream like Pythagorean theorem to you, but remember that you could rewrite this as dx over the square root of x squared plus 1 all raised to the 3rd power, right, cubed. So when I see that square root and I see a plus sign and two things underneath of it, right, that screams a squared plus b squared to me, so that means that this is going to be our hypotenuse, right, based on the Pythagorean theorem. So again, we'll draw my reference triangle going this way. Doesn't matter. So this is going to show up on my hypotenuse then, and that means that the two legs have to be x and 1, so that way you have a squared plus b squared equals c squared. So when I go ahead and do that, now it's just kind of figuring out where I want my theta to be. So the easiest way to solve for this thing is if I relate this side and this side. So we have a couple of different options, right? Remember, you want to use sine, secant, or tangent. So I'm going to go ahead and say, well, let's just put our theta down here. And then I'm going to have that this is the hypotenuse, this is my adjacent and my opposite, so this is going to be a secant problem. So I'm going to let the secant of theta be equal to the square root of x squared plus 1 over 1, which is just the square root of x squared plus 1. So now I can replace this thing with secant of theta. So I'm going to get the secant of theta all cubed in the bottom. And then I need to replace my dx. So the easiest way for me to replace my dx is going to be if I relate my x and my 1 together. So based off of where those are, that's going to be my tangent function. So the tangent of theta is going to equal x over 1. That's super easy, and that just tells me that if I take the derivative, secant squared of theta d theta is going to equal dx. So I'm just going to go ahead and replace all of this for my dx. Okay, so now if we go ahead and simplify, right, secant squared over secant cubed is just going to be d theta over secant. But 1 over secant of theta is just the cosine of theta. And the integral of cosine of theta is just the sine of theta plus c. And then if we look back at our triangle, right, the sine of theta in our reference triangle is opposite over adjacent, so that's going to be x over the square root of x squared plus 1. So this is going to turn into x over the square root of x squared plus 1, all plus c. So not too bad there. It worked out pretty simply. I'm just going to start a new page here. We're going to look at our final example. Okay, so for our final example, we're going to look at the integral of dx over the square root of x squared minus 4x. So I see a square root, and I see two things with a subtraction sign in between it, but it doesn't quite fit that Pythagorean format because I can't really rewrite 4x as a perfect square. I can rewrite the 4 as a perfect square, but the x doesn't work out so well because you really want a constant and a variable spot. You don't want the variable to be in two different positions. So this means, right, we got to rewrite this. So we're going to use completing the square to turn this into, we call this u squared minus a squared form. So you only want the variable in one spot. So I like to complete the square by taking whatever I have and setting it equal to 0. And I put the blanks there to help me figure out that I have to put it on both sides. So to make the left side a perfect square, I'm going to take my b value, -4, and divide it by 2, and then square that. So -4 over 2 is -2. -2 squared is +4. I'm going to rewrite this as a perfect square binomial, right? X minus 2 squared gives me that thing. And that equals 4. And then I'm just going to move everything over to one side so it's equal to 0 again. And so I can replace this now and make this the integral of dx over the square root of x minus 2 squared minus 4. And so now that looks a lot more like it's a Pythagorean theorem form. So we have a minus sign, so that tells me that we are going to have the thing in front of the minus sign on the hypotenuse. So I'm going to put the quantity of x minus 2 here, and then that means that my 2 is going to go on a leg. So I'm just going to go ahead and put that here. Doesn't really matter. And then if I were to do my Pythagorean theorem, right, I would get the quantity of x minus 2 all squared minus 2 squared, which is 4. All square rooted is the vertical leg. It's just the other leg, whatever leg you want to put it on. Doesn't matter. Okay, so now we need to figure out how we're going to replace all of this. So remember, our goal is to think about sine, secant, or tangents. So to replace this, I want to just involve that. So I want to involve this side and then my constant side. So that's going to be really easy to solve for. And that's going to clue me in that my theta should go here because then this is opposite and adjacent. So then I get tangent. So the first thing I'm going to define is that the tangent of theta is equal to the square root of x minus 2 squared minus 4 all over 2, which tells me that 2 times the tangent of theta is equal to that radical that we want to get rid of. So I'm going to go ahead and start by replacing with that. So this is going to become 2 tangent of theta in the denominator. And then I want to replace my dx. So my easiest thing to relate for those two parts is I want to relate the constant and then the side that's easier to solve for x. So I want to relate my adjacent and hypotenuse, so that's going to tell me cosine. But I want the variable to be in the numerator spot, so I'm going to actually use secant here. Right, because remember, secant, cosine, right, they're just reciprocals. So the secant of theta is going to equal the hypotenuse, x minus 2 all over 2. Well, that means that 2 times the secant of theta is equal to x minus 2, or 2 secant of theta minus 2 is equal to x. Okay, so now to find our dx, take the derivative of both sides. This becomes 2 secant of theta tangent of theta. D theta is going to be equal to dx, right? Because the derivative of that constant 2 is just 0. So we're going to go ahead and replace this stuff with this stuff. So we're going to get 2 secant of theta tangent of theta d theta. Now this is super convenient because the 2's cancel out and the tangents cancel out. So our integral is going to become just the integral of secant of theta d theta, and we know the integral of secant is just the natural log of the absolute value of secant of theta plus tangent of theta, and then plus our c on the end since it's indefinite. Okay, so now we just have to replace. Well, we know that from our original substitutions that secant of theta is the quantity of x minus 2 over 2, and the tangent of theta is the square root of quantity x minus 2 squared minus 4 all over 2, then plus c. Now that is a perfectly fine place to leave your answer, but we can make it actually look a little nicer using our log properties. So I'm just going to change colors so that way we can see that you can also rewrite it using this. We can combine those two fractions in there to be x minus 2 plus the square root thing. Right, common denominator was a 2. And then if we use our log properties, this becomes the natural log of the quantity x minus 2 plus the square root of x minus 2 all squared minus 4 minus the natural log of 2 plus c. Now, this is just another constant. So we can actually, if my pen would write, there we go. We can actually absorb that into our plus c at the end. And we can make our final answer the natural log of x minus 2 plus the square root of the quantity x minus 2 squared minus 4, all plus a different c value, right? So that this would be like c1 and this would be a c2, where c2 is equal to negative natural log of 2 plus